Class we were discussing about the phase stability, the metastable states, under what conditions we expect the states to be stable and for them to be in equilibrium. So just a recap of what we did in the last class. We found that for a liquid which is heated at a constant volume, so let us suppose that initially we are at state B here. And if we are heating this liquid, it means that we have to plot one more isotherm. This is the ideal case, but it will have some metastable states as well, whose lowest point will be on this spinodal curve. Let us suppose that it also follows this path. We have one more isotherm and its spinodal curve also follows the path as I have shown in this diagram. Okay. Sorry, I've just made it wrong. Yeah. Right. So if we are heating the liquid at constant pressure, let us this we are doing just to establish the equilibrium conditions here. So let us consider a system which is at initial state. This liquid is of course at metastable state. So this is a superheated liquid and its temperature is TL and the pressure here is PL. Now since we have mentioned that this liquid is at metastable state, so if we go by our PV diagram, we know that this pressure here of liquid, it would be less than that of the saturation pressure at temperature TL, right? So that is the condition we have. And let's suppose that then the embryo formation takes place. So now we have an embryo which is a very small vapor having the same temperature TL, because we are assuming the equilibrium conditions, and since we are assuming equilibrium conditions, it will have the same chemical potential. So we can see that mu L is equal to mu V and TL is equal to TV, where TL is the temperature of this superheated liquid, TV is the temperature of the vapor, mu L is the chemical potential of the liquid and mu V is the chemical potential of the vapor. But now we have observed the bubble, so it means that the pressures, they cannot be equal because of the excess pressure, because of the radius of this curvature. So we'll have a excess pressure, and that we can write as PVE minus PL is equal to 2 sigma by RE. Here sigma is the surface tension and this RE is the equilibrium radius. Now considering the Gibbs-Duhem equation. So Gibbs-Duhem equation is an equation which relates the three thermodynamic state variables, which are the mu, the T and P. So this is the Gibbs-Duhem equation, and now we are integrating this Gibbs-Duhem equation over a constant temperature, because we know temperature of a vapor is equal to temperature of liquid here, TL. So it means that here this dt term would vanish and we are just left with du is equal to VdP. Now integrating this equation, what we will get between the saturation point P sat and any arbitrary point, let us suppose this point to be P. So it would give us this expression, which is mu minus mu sat is equal to integral of P saturation at temperature TL to arbitrary pressure P at any point times VdP. Now we know that in our system we have both vapor, we have both liquid. So let us find out what would be the mu for vapor phase and what would be the mu for liquid phase. Here we are considering an assumption that this follows the ideal gas law. So it means that we can write V is equal to RTL by P, or let's call it PV, and then if we integrate this between P saturation to P, here it's P, it's PVE, what we'll get is RTL ln of PVE by P saturation at temperature TL. So that's what I've written here. So we can then say that chemical potential of the vapor at equilibrium is equal to the chemical potential of the vapor at saturated state, which is in the vapor dome. If you look at a vapor dome, it would be somewhere on this line plus RTL times log of PVE plus Psat at temperature TL. Similarly, we can do for the liquid, but we know that liquids, they are incompressible. So it means that volume, they are not a very strong function of pressure there. So simply we can write it as mu L is equal to mu saturation liquid plus VL, which is the volume of liquid or specific volume of liquid, times PL minus P saturation at temperature TL. Right? Now, since these are in equilibrium, what we can say is mu L is equal to mu VE. That is the first condition. It means that we can equate the right hand sides of both these equations. And further, governed by the thermodynamics laws, we can also say that mu saturation at V must be equal to mu saturation at liquid, because the phase change here is in equilibrium. Ultimately, what we'll get is RTL log of PVE by P saturation at temperature TL is equal to VL times PL minus P saturation of TL. Right? So here what we are trying to do is we are trying to find the vapor pressure. What is the pressure inside the vapor at equilibrium? So this I think we have covered. Yes. So using these two equations, what we get is P of vapor is equal to P saturation at temperature TL into exponential of PVL times PL minus P saturation at temperature TL by RTL. Now let me ask you, out of these two terms, which term would be greater according to you? One is the pressure inside a vapor at equilibrium, one is the saturation pressure. To go there, let us first have a look at this term here. We already know that PL would be less than that of P saturation, because we are talking about the liquid which is at metastable state, and at metastable state the temperature would be less. Sorry, the pressure would be less. Right? It means that this term would always be a negative term. The other terms inside this bracket, they are all positive terms. And exponential raised to the power negative is less than 1. It means that your PVE, it must be less than P saturation at TL. What is the significance of this statement? The significance of this statement is, let's suppose that the vapors, they are formed at pressure PVE, right? And we are talking at a constant temperature, so temperature is TL everywhere. It means that if initially the liquid is at some metastable state here, for a temperature TL, its saturation point is here, right? And it is greater than the PVE. It means that whenever the phase change occurs, it doesn't occur from a metastable state to a metastable state. Always the vapors will be in a superheated form. So if perturbations are given here, we'll expect the vapors to be in a stable vapor or in a saturated vapor region. It's not possible that from this metastable state we can see a jump to a metastable state. The system, it always tries to go towards a stable state, having lower value of delta G or lower value of mu. So this is what one insight which you get from this expression here. Now next is using the Young's Laplace equation, which is PVE minus PL is equal to 2 sigma by R, and then this expression for PVE, we can find the bubble radius at equilibrium. So using this, what we can do is we can simply use PVE minus PL is equal to 2 sigma by R at equilibrium. Then R equilibrium would be equal to 2 sigma by PVE minus PL, and that we can then we can maybe put this PVE, the whole expression here, and then we'll end up with this term. So this would be the radius if the system is in, if the vapor is, for the vapor to be in equilibrium, it must have this radius. Of course, next we will see if this equilibrium is stable or unstable, or whether if any perturbation take place, what will happen to the system. But for now, this is the equilibrium radius and that we have found using the Young's Laplace equation, as well as the correlation between the pressures and all the pressures here. And this is where the vapor is surrounded by a metastable liquid. Yes, so next is that your PVE minus PSAT is much less than, this is assumption which we take, but later we will find when we will plot the mu versus P diagram, we will see that this is true, that this is much less than your 2 sigma by R. It means that we can neglect this term here. So this will be just neglected in comparison to this term, and we will see PV is equal to PSAT. A much simplified expression is that what we have now. Right? So let us try to do one simple problem. In this simple problem, of course you will not solve it here, I will just write some numbers and then we will see what insights we get from this problem. So we have already seen that your RE, or radius at the equilibrium when the vapor is in metastable liquid, it can be given as 2 sigma times P saturation at temperature TL times exponential of, let me see, VL times PL minus P saturation at temperature TL minus, into by RTL minus PL. This is the radius at equilibrium. Now in this question what we are being asked is that determine the equilibrium radius of a bubble in equilibrium with the superheated liquid. It means it's a metastable liquid at temperature 120 degrees centigrade and atmospheric pressure. So for this we need the we need the properties of the liquid at 120 degrees centigrade that we can get from the steam tables for saturated water temperature table. From here we can see that what is your pressure, saturation pressure, what is your saturation liquid volume, and all these parameters. And in the end what you will get is that RE would be equal to 1.2 micrometer, which is 1.2 into 10 raised to power minus 6 meters. So if your metastable liquid is at 1 atmosphere and 120 degrees centigrade, its equilibrium radius would be somewhere in the order of 1.2 micrometer, which is already very small and it's not visible by a naked eye, right? Now if I change the temperature, let's suppose that I want to see what happens if temperature is a little bit lower. So if temperature is 105 degrees centigrade, using the same equation you can see that the equilibrium radius would comes out somewhere around 6 micrometer. If we increase the temperature just by 15 degrees centigrade, this lowers to 1.2 micrometer. If we further increase this to 150 degrees centigrade, it becomes almost 5 times. So it is around 283 nanometers. And if the temperature is around 250 degrees centigrade, it turns out to be just 13 nanometers. So this is what the equilibrium radius of the vapor bubbles would be if that bubble is formed homogeneously inside a metastable liquid. These are just numbers so that you can see that as we increase the temperature, the radius is reducing at a very fast rate, right? Yes, so this curve we have seen in the last class. It is simply the mu versus P plot, where mu is the chemical potential and P is the pressure. So this curve we derived using the, or we didn't derive, but I just put an assumption that we are assuming it to be a van der Waal, this fluid to follow a van der Waal equations, and then the point A is the point, or I can just write it here. point line AB is a line of stable liquid region. Line BC is the, anyone, what is BC? You can also use this curve to find out. BC is, in BC is the liquid stable or metastable? It's metastable, right? So BC is a superheated liquid. Further, line FG is your stable or superheated vapor. Similarly, line EF is your supercooled or metastable vapor. Right? Now, as you can see that if, let's suppose we are heating a liquid and that liquid is already in state A, this state A is a metastable state. Now, for this to be in equilibrium with the bubble, their mu must be same. So it means that system can only be in equilibrium when both the liquid and the vapor, they are in superheated form. As we can see here that we have a constant mu, so they can only be constant, this system can only be in equilibrium when both the vapor and the liquid, they both are in superheated form. Now, I think one assumption we also took in the last 2-3 slides ago, that assumption was PVE minus P saturation at temperature TL is much less than 2 sigma by RE, and that you can confirm from this plot here. So here this PVE is the pressure of vapor and P saturation is the saturation pressure at temperature TL, and this PL is the pressure at superheated liquid. So if you see just the magnitude, so this PVE minus PL, which is, I can write it here, 2 sigma by RE, it is much less than that of PVE minus P saturation. So this our assumption, it holds true there. Now since we have established the condition that for the vapor to be in equilibrium with the liquid, they should be in a superheated form. Let us also try to see if this equilibrium is stable or unstable, whether the vapor, the bubble will sustain, it will grow, it will shrink, what will happen to bubble, that we will discuss now. So for that also, what we do is we take the system where we have a liquid at temperature TL, and this TL is a temperature of superheated liquid, and we have pressure PL. Of course, this pressure is less than the P saturation at temperature TL, and then we have an embryo of vapor which is having pressure PV and temperature is TL here. Now, to see if this is stable, what we do is we take the Helmholtz free energy here. Now, Helmholtz free energy, usually defined by A or F, is equal to U minus Ts. Now, here we are talking about the case where temperature is constant, right? And you can see that U and S, the internal energy and your entropy, they both have additive properties. It means that it is possible to write this F by disintegrating this into F of liquid, F of vapor, and F at interface. So what we can do is we can write F of interface plus F of your liquid plus F of your vapor is equal to F. So that's what we are doing here. So then we can write FL, that Helmholtz free energy of the liquid, it can be written as NL. NL is nothing but the number of moles of liquid. Number of moles of liquid. Similarly, NV is the number of moles of vapor. Mu L is the molar specific internal energy, and SL, this hat, is molar specific entropy of the liquid. So we can write this FL as NL times UL minus TL SL, and similarly we can write FV as NV times UV minus TL SV. For interface, we require excess energy to create an interface, and that depends on the surface tension or surface energy. So for that we can write Fi is equal to 4 pi r square, which is the surface area of this vapor bubble, times the sigma I. And when we add all these terms, we get this simple expression, which tells nothing but the Helmholtz free energy of the system we have. Now considering the Gibbs energy here, we know Gibbs energy is U minus Ts plus PV. We can simply write it as this term as F, so F plus PV. Now to define the volume of the system, we can also write it as NLVL plus NVVV, where NL is nothing but number of moles of liquid and VL is the molar specific volume. The subscript here represents whether we talk about the liquid or the vapor. Right. So further using this equation, what we get on I've just written a simplified equation here, but what we get is G is equal to NVGV plus NLGL plus 4 pi r square sigma I minus NVVV times PV minus PL, where these GV and GL are the molar specific Gibbs energy for both liquid and vapor phase here. Now let's talk about the phase when the bubble was not formed, because we want to see how much is the change in the Gibbs free energy. So when the bubble was not formed, we can write the Gibbs free energy simply as at that time it was totally liquid. So the specific molar specific Gibbs free energy of liquid times the number of moles in the entire system that include both of vapor and liquid. We can write G naught is equal to NV plus NL into GL. Now if we try to find what is the change in the Gibbs energy, which is the final minus initial, we get to this expression, which is delta G is equal to NV times GV minus GL plus 4 pi r square sigma. This is simply I've written this equation and subtracted this equation from this equation. So we get a much simplified this term. Here we had NV and GV separately, we have a much simplified this term, where I think now we don't have the term of NLGL. So yeah, this is what we get. Now for a pure fluid having just one component, we can write that chemical potential is equal to its Gibbs free energy, because we know that mu is nothing but del G by del N at constant temperature, and since it is just one phase system or it's a pure fluid, so we can say that mu is equal to G. And for the bubbles to be in equilibrium with the surrounding liquid, this one we have already written previously, which translates that the Gibbs free energy or the specific molar specific Gibbs free energy for the volume would be equal to the Gibbs molar specific Gibbs free energy for the liquid. So using this and further using the equation for volume of bubble, which is 4 by 3 pi r square, what we get is we get delta Ge, delta G at equilibrium is 4 by 3 pi r e square sigma. We have done nothing, we have just simplified this equation which we derived in the last slide. So this term would simply vanish because we are talking about equilibrium here, and then we are just simplifying both these terms. So delta G at equilibrium is 4 by 3 pi r e square sigma I, and this is your delta G. This is of course this is not at equilibrium, this is an equilibrium. So yes, from this expression what you see is that on what variables does delta G depends. So delta G from here, it is a function of course your GV and GL, and GV is a function of both TV and of course TV is equal to TL, and one more term I believe, yeah, PL. It's further a function of PV, and it is also the function of R, and it is also the function of VV. On this all terms the change in Gibbs energy depends. Now these two terms, they are kept constant for the system initially. So it means that we can remove these terms from delta G expression. Further, uh, we can simply use the ideal gas law to see that Vv is equal to RTL by your PV. So it means that it will just depend on one of these two because these two are interconnected. And then using the Laplace equation, we can see that your PV is already a function of radius. So it means that delta G is just a function of your radius here. So now again expanding the delta G here, the Taylor expansion of delta G around R is equal to Re, what we get is delta G is equal to delta G at equilibrium plus d by dr of delta G at R is equal to Re times R minus Re plus so on so. So we have just expanded the expression for Taylor series of delta G around about R is equal to Re. Now if we try to find the del G by del R so that we can know that if that's a point of inflection, so we you can see that d of delta G by dr at R is equal to Re comes out to be 0. It means that this is a point of inflection. Now to see if this point is the point of maxima or minima, so that we can know that our Gibbs free energy is maximum or minimum that point, we take the double derivative. And when we take the double derivative, what expression we get is minus 8 pi sigma I by 3, 2 plus 1 over 1 plus 2 sigma I REPL. Now in this expression, complete expression, all the terms they seem to be positive. So it means that this is less than 0. It means that this is a point of maxima. So having a point of maxima in the Gibbs free energy, it means that this state is unstable state. So it means that whenever the homogeneous nucleation takes place inside a superheated liquid, that at Re is an unstable state. I think further we have simplified this expression here to just find what is the value of my final delta G by delta GE, and it comes out to be in this form. And usually at smaller radii, this term is very large, and if this term is very large, so it means that this can be very small in comparison to 2. So this term can then vanish. Anyways, this is what we get, the change in entropy, change in Gibbs free energy. So at R is equal to Re, from this equation here, we get this plot. Basically we get this plot just about Re. So we only get this solid plot here, yet we don't know what are the possibilities on the dotted side of the curve. But of course we know that this is not a stable, this is an unstable equilibrium. If any perturbations happen here, the system will try to spontaneously go towards the more stability, right? Now what we expect here, let's suppose that if your Re approaches to infinity, if your R approaches to infinity, if your R approaches to infinity, what could happen? The phase change could occur, the complete phase change is over, right? It means that that could be a spontaneous process. So we'll see that we can just demarcate it by dotted line that as R increases, your delta G, it reduces and it may go to a minima point. If your R, it approaches to 0, it means that your liquid is at metastable state. It means that no phase change has occurred. It means that there is no change in Gibbs free energy. It means that it will approach to 0 here. So we will just solidify this, we will just draw this line, and this is a complete curve for your delta G versus R. From this curve, from this graph, what insights we get is that, let's suppose that you are sitting at this point here. At this point your radius is Re, and let us suppose that the embryo has n number of molecules. Now if you remove just one molecule from that vapor embryo, it means that now we are at state of R less than Re. By just removing one vapor molecule, the system will spontaneously go to 0 state. It means that the bubble will collapse. So here the bubble will collapse. It means that boiling will not, or the bubble will just collapse. Collapse will not have bubbles for that equilibrium radius. Similarly, if this vapor embryo, we add one excess molecule to that vapor embryo, it means that at that time we'll reach R greater than Re, and the bubble will spontaneously grow and then the phase change will, and the boiling will start to occur. So in that case, we'll follow this path here, and the phase change will occur, right? So, and this is, yes. So in the last class, what we assumed the mechanical equilibrium, but we know we are not talking about a bubble. It might happen that the fluctuation in the pressure is so high that the bubble is not able to maintain its shape, right? The forces changes are so rapid that your assumption that PV minus PL is equal to 2 sigma by R, it doesn't hold off, right? So if the force changes they are too quick, then the mechanical equilibrium might fail, but in that case the potential equilibrium is a better assumption, which we have taken in this beginning. So in that case the potential equilibrium is a better assumption, and then we have proved that why it's a better assumption, because it might happen that the force changes are so rapid that mechanical equilibrium cannot sustain that. So regardless of assuming chemical or mechanical equilibrium, stability of bubble remains a qualitatively similar for both these cases. Now I think okay, so maybe the problem is later, but now let us jump on to the kinetic limit of superheat. So far the discussion from previous studies, they indicate that the likelihood the homogeneous nucleation will occur will depend on the kinetics of the bubble embryo formation. How the bubbles they are formed, that will govern the kinetic limit of the superheat. Any embryo that have n number of molecules is continuously losing molecules due to the condensation, and the same molecule is again gaining the number of molecules because of the boiling which occurs at the interface of these bubbles. So for that, let us consider again a superheated liquid. So this is a superheated liquid which is at temperature TL and the pressure is PL here. And we assume that the fluctuations occur so fast that these fluctuations they reduce the density of the liquid, metastable liquid, and then we observe the formation of these bubble embryos. So now these bubble embryos are formed. They can be of different sizes, having different number of molecules, but these embryos are formed because of the heterophase fluctuations. Now if we have to give the size distribution of these vapor embryo bubbles, of course it will be a function of Gibbs free energy. So we can write it as Nn is equal to rho NL times exponential of minus delta GR by KBTL. So here Nn is the number of molecules having small n number of vapors molecules. So capital N here represents number of embryos and small n represents number of molecules in that embryo. So it simply defines the particular population. Rho NL is the density of number of embryos in a liquid into exponential of minus delta G by KB TL. Here delta G is negative. Can someone tell why we are using negative sign here? We are using negative sign here because for a spontaneous process, this delta G it should be a negative, it should reduce. So if we want to see the more population, then negative signs must be there to compensate for that. That's why we are using negative sign here. And we also know that equilibrium distribution is established only if for a particular population class, if the number of molecules in that class is evaporating, the same one is boiling back into the phase. So we can simply say that if this is your bubble, the number of boiling which occurs at this interface, it must be equal to somewhere else where the condensation takes place on this interface, so that for the particular number of molecules of the embryo they remain same. So what we can write for this equilibrium to establish, we can write that Nn, which is the number of molecules having small n number of molecules, times An is the area of this interface, Jn is the rate of number of molecules that are evaporating from that bubbles. That must be equal to the bubbles having n plus 1 number of molecules into the area of those bubbles having n plus 1 number of molecules times the rate at which the vapors they are condensing onto the interface, so that at the end we have same number of molecules of Nn. This is what the equilibrium definition here is. Now, for a real superheated liquid, the system is not to be expected at a because boiling is not an equilibrium process, it is a highly non-equilibrium process. So we cannot expect that the system is always be at equilibrium. So for that, what we define the GIAN. GIAN is the number of molecules, excess number of molecules for certain class of population of the number of molecules. So GIAN can be defined as n star n an JNE, where this simply represents the from how many number of molecules, from how many number of embryos the evaporation is taking place into the embryos, and n plus 1 here represents from how many interfaces the condensation is occurring, so that the bubble is again increasing in size, right. So and then their difference, it tells us how much excess of number of molecules we have from n to n plus 1 and how much excess of molecules we have from n plus 1 to n in terms of both evaporation and condensation respectively. So using this equation and using the previous equation, which was simply Nn An Jne is equal to Nn plus 1 An plus 1 Jnc. Using both these equations, what we can get is, we get this Jn in terms of n star and n. And next what we are going to do is, we are going to write this term as a continuous variable. We are treating n as continuous variable, so that it becomes easy for us to do the mathematics here. So we can write Jn simply as minus of Nn An Jne times del of n by dn, and for the rate at which number of molecules are changing, we can write it again as dn by dt is equal to minus Jn by dn. Now to keep our analysis a much simplistic, we can assume that the embryos, they are continuously forming and they are growing, but the rate at which the embryos enter and leave each size class is balanced. It means that this term would be 0, so that the population, it stays same for each class of the embryo size. So we can simply put it as 0 and we will get Jn is a constant. So now Gn, we defined it as how much excess molecules we have, that remains constant. So it means that we are talking about bubbles having let us say diameter of 1.2 micrometers, then that vapor bubbles number would always be same in the system. Let us suppose in a system we have thousands of molecules, among those 1000 molecules we have 100 molecules of 1.2 micrometer, that number should remain constant. That is what we are imposing here. Now if an embryo is bigger than the critical size, it means that it is somewhere on this delta G R curve, it is somewhere here. It will keep on growing spontaneously, so as to for the boiling to occur, right. But let us imagine a state which is just when we totally have a superheated liquid. We do not have any bubble embryo having size more than the critical size. In that state, what we can say is that the number of embryos would be 0, because if there are some embryos present, then that would lead to the phase change. It is a spontaneous process. So what we can write is that n star would approach to 0 as your n is close to your n equilibrium of bubbles. We can also plot it using this graph here. So here n is the number of molecules and n represents the number of embryos, and we can say that at non-equilibrium it would be close to 0. Of course at equilibrium, because it is just the inverse of Gibbs, so we will have certain number of embryos which are having the size of Re, they will be at unstable equilibrium, but still they will be present. But for non-equilibrium state, it will be close to, it will be almost 0, because if it is not 0, then the phase change would occur, and we are talking about the case where we still have a superheated liquid. Further, as n by n approach to 1, as n approach to 0, what does it mean is that as the number of molecules in an embryo class is getting reduced, it means that we are having very small number of embryos, small size of embryos, multiple embryos. In that state, it doesn't matter if that is equilibrium or non-equilibrium state, because the number is so high that they are almost comparable. So in this, when n is approaching to 0, it means that the number of embryos in equilibrium and non-equilibrium state, they are almost equal. That's why the ratio it approaches to 1. So we can have this plot where this is for your equilibrium and this is for your non-equilibrium. Further, using the same equation where we have assumed n to be a continuous variable, and further integrating and rearranging using the kinetic theory of gases, we get this equation here. So this equation is rho NL times 3 sigma by pi m exponential of minus sigma by sigma cube upon 3 kb TL PV minus PL. Now, if you look at this J, the term which is inside the exponential, that is a strong function of temperature. TL is here and pressure is also a function of temperature. So, if any fluctuation, if any changes take place here, this J can be, we can see a very sharp increase or sharp decrease in J, and that is what we see. So, if we have a look here, we can see that J is defined as a rate at which embryo bubble grows to the size n to n plus 1 molecule in a unit liquid of volume. So, if J was defined as the excess number of molecules, so the molecule which grow from size n to n plus 1, that is given by this J. And you can see in the term of J, there is nowhere we have n here. So, it means that it is constant for across all the size of embryos. So, we can say that J stays same for all n, and it is also a rate at which the critical size bubbles, they are formed. And the higher the value of J, the higher the chance that bubble will cross the critical size and grow its own. That is the case of probability. If we have the higher number of excess molecules, the probability of them crossing the size, the size from which it just grows on would be higher. What key insights we get from the kinetic limit of superheat is that most temperature effects, they show up inside exponential term, as we discussed. I can also discuss it here, that mostly all the temperature effects, they show up inside this exponential term. So even if we increase the temperature by 1 degree Celsius, we can see there's a boost of the embryo formation by orders of magnitude. So at one state you can see that there is no embryo formation, but even if you see the increase by 1 degree Celsius, we can see that multiple embryo formation can occur, and that too in multiple numbers, multiple orders of numbers. Also, the nucleation rate, it increases sharply with temperature, meaning there is a narrow temperature range where below it, I mentioned it already, below which we have almost no nucleation, and above it the nucleation happens instantly, and we can see a lot of population of these embryos happening there, which then further leads to, which then grows and the phase change occurs. And the median, it's not midpoint, it should be median. The median of this range of temperature is called the kinetic limit of superheat. Okay, so this is a very small homework for you. What you can do is estimate the kinetic limit of superheat for water at 1000 kPa and see what it comes out to be. Of course, you have to use the same relation for J, very simple, but you have to look out for the saturation table or the steam tables, and then you have to see how it comes out to be. This plot here, it shows J versus TL. Now, as J is defined, J is the number of excess molecules per unit volume per rate. It's a rate, so it's per unit time. So you can see very clearly here that let's suppose that we talk about water. Water at 101 kPa or is the pressure, and when the temperature is around, let's say 298 degrees centigrade, the number density is almost 10 raised to the power minus 10, so small. But as you increase the temperature incrementally, maybe somewhere around 307 degrees centigrade, almost 9-10 degrees Celsius increase, you can see that the excess rate of formation of embryos, it just jumps from 10 raised to the power minus 10 to 10 raised to the power 20. That is almost the jump of 10 raised to the power 30 in terms of orders, massive. So here if we take just 1 cube of water, the rate would be 10 to the minus 10, very low rate. But as we increase the temperature beyond 306, 305 degrees centigrade, we can see that this jumps to a very high number. So this is all governed by what kinetics we have when we talk about the metastable liquid and what leads to the formation of bubble embryos there. This part is also a homework for you. So whatever expressions we have used, the same can be applied for a reverse system. Reverse system means that we have a liquid droplet here and we have a vapors here. In our system, we had a bubble here and we had a liquid here. So this vapor would of course be at a metastable liquid, it will be subcooled liquid, and then we will see that at what the nucleation of droplets starts to take place. And similarly, you can from here you can reach to this point. That you must do as a homework, just as a reading assignment. Just read it somewhere from the book. The book is VP Carey. You can have a look at this, and all the expressions they remain same. But this is just a reverse system. So next we'll discuss very briefly about nanobubbles before we end this lecture. So as the name suggests, nanobubbles, it means that these bubbles, they are nanoscale in size. So they can be gas bubbles or the vapor nanobubbles, but nanobubbles, they represent a very outstanding problem in surface science or in soft matter physics, that these bubbles, they exist. Why these bubbles exist? If you just simply calculate the Laplace pressure, and you see this R is in the order of, let's say, 10 to the power minus 8. This pressure, it comes out to be in megapascals. Such high pressure, still these bubbles exist. So that is a very important question, and many researchers, they are trying to work on this question. These bubbles can be vapor bubbles and gas nanobubbles. Gas nanobubbles, it's usually easy to nucleate, but vapor nanobubbles, they are quite difficult because usually what we see is that nucleation occurs on the surface. So vapor homogeneous bubbles, they are quite difficult to nucleate. And these bubbles, they have shown, especially the gas nanobubbles, they have shown very high stability and longevity. Sometimes these bubbles, they are known to be stable for several weeks. Even though if we use a classical Rayleigh-Placid equation, we can see that the time scales, it comes out to be just 0.1 milliseconds. Yet these bubbles are stable. So this is still an outstanding question. Some researchers, they point out that we have a lot of contamination around these bubbles, which stops the gas diffusing out of the bubble. There are several theories, contamination theories there, and pinning theories there, a lot of theories are there, but still these bubbles, they should not exist, yet they exist for a very high times, even though it predicts that the time should be very small, because the Laplace pressure is very high. And these are some bubbles on which I worked on. So maybe I can show you this movie. So this is a movie of bubbles nucleating. Okay, so I think I have to switch it off, and yeah. So just look at this scale. This is 200 nanometers. So these bubbles are in the order of around 50-60 nanometers. So these bubbles are nucleated in a liquid when we irradiate the liquid using electron beam. So what happens is that electron beam, it dissociates the water into various radicals and hydrogen molecules. And when the hydrogen molecules, the saturation increases, then these bubbles are nucleated on the surface. So these are the gas nanobubbles which was observed. And I also recommend you reading, there's a lot of literature on these bubbles, various groups working on that. So you can read these literature on these bubbles. And of course, we will continue this discussion in the second half of this of what we have from 2 p.m. One thing I would like to highlight here is that this is a graph which shows the variation of number of bubbles for a specific radii, number of bubbles of certain R in a volume, in a per unit volume. So this NR just represents number, and here we have a radius of the bubble. For a liquid water which is at 101 kPa and 120 degrees centigrade, the RE, it comes out to 1.2 into 10 to the power minus 6 meters, which we already discussed in the beginning. But you can see that the probability of having, or the number of nanobubbles in the size less than 1 nanometer is very less. So it means that if your volume is around 10 raised to power minus 40 or 10 raised to power 40 meter cube, you can have just one bubble there, right? So the probability of observing nanobubbles is very low. Similarly, you can see for various temperatures that this is for 180 degrees centigrade. You can see that the number of bubbles are very less. For RC is equal to 9.8 and temperature 180 degrees centigrade, we can see that the size of the bubbles of this range, their number would be very less. But this also points to one more thing. You can see that this graph is decaying very fast. This graph is decaying very fast, and it might happen that this graph is not able to reach here. And this is a point where the radius of the bubbles or the radius of the homogeneously nucleated bubble is present. It means that in actual cases, homogeneous nucleation is almost impossible. We can't see homogeneous nucleation because for homogeneous nucleation to occur, this bubble, if we solve this equation further, we should get somewhere here, and here the number density is very low. Almost if we have 10 raised to power 250 meter cube of water, we can see one homogeneous nucleation. So mostly that's why we see heterogeneous nucleation. Before closing, I will just discuss one case here. So this is the work which is done by Dr. Soumyadeep Paul, and I happened to work with him for a short time. What he has observed, he has tried to do the homogeneous nucleation of the vapor nanobubbles. His system in such a way that he has a nanopore, and we have two electrodes, one on top and one on bottom, and he is using electrolyte here. So when we put a certain voltage across this nanopore, what happens is that there is a flow of ions, and because this nanopore is so small, its radius may be 150 nanometers, that because of the resistance of the flow, we observe a massive Joule's heating happening here, and that Joule's heating is so localized that we observe the homogeneous nucleation before the heterogeneous nucleation. So what he has seen, he has observed the homogeneous nucleation to happen even before the stable film or the nucleation on the side walls of these nanobubbles take place. So please, you can go to his work. His work is published in PRR, and it is on the thermodynamic bifurcation of bubbles inside a nanopore. Yeah, so I think time is almost up. So we will continue with nanobubbles and how to observe these nanobubbles, both the gas bubbles and the vapor nanobubbles, in our session, which starts from 2 p.m. So that is all for today's lecture. If you have any questions, we can have discussion right now. Else we'll meet at 2 p.m. But yeah, even though we have studied this homogeneous nucleations, as we have seen in the last slide, that it is almost impossible to observe this in real life, because the energy for the surface to form a homogeneous is very high, because we are creating a whole bubble there. In the heterogeneous nucleation, we just see it just occurs on the surface, right? So that's all.